All right. Okay, so we can start by you asking questions, whoops, or we can start just by me spouting off what I think might be helpful. What do you want to do?
Can I ask you a question about the quiz?
Well, yes.
Not like the answer, but like.
No, you know, the quizzes are, oh shoot, I don't have any markers. This one works. Oh, well, we'll have to do. The quizzes are all screwed up. I've been trying to fix them. I don't know how. So.
As in like the answers?
Yeah, like
okay.
even though you have the right answers, they're not giving you, they're not telling you it's the right answer. So everybody that's checked with me had the right answer, and it was just the quiz that was the problem.
Okay,
So
I just took it on a 0 out of 50.
yeah, so if you just take it, I'll give you full credit. But I realize it's really frustrating for that to happen. So I'm going to continue to try to fix them. I don't know. I can't figure out what's wrong.
Or the answers that people sending to, were they close?
Well, that's what I'm changing. I've changed the tolerances on the answers, and that didn't seem to help.
Yeah.
So so I must have done it wrong, and I actually think I made it worse with how I fixed it. So
It's scary. I took it this morning, I got a 0. Like some of them are just simple plug-in.
right. So so please forgive the frustration. I'm going to try to work on it this weekend. If I can't fix it by the end of this weekend, I'm just going to tell you not to take them, and maybe look at the questions so that you know what I'm expecting. But then we can work out. Everything that's in the quizzes is in the homework. So
if you end up doing that, is there any way you could post the answers just to see?
well, the problem with the way they're set up is that the numbers are different for every student.
Sure.
Maybe
So.
like a variable setup.
So yeah, so you know what I'm going to do? I'm just going to set it up so that there's no variables. Everybody just has the same numbers. Who cares, right? It's not like, yeah, that's what I'll do. That's how I'll fix
That's
it.
just like knowing, practicing.
Right, I don't blame you. Yeah, okay, I'm going to work on that this weekend.
Or switch it to like maybe multiple choice, then would that make that life a lot easier? Multiple choice
Yeah,
answers,
I
then
don't know
that
if
way
I'm going to
there
spend
is.
that much time.
Well, I'm just saying that then there wouldn't be any.
It might be easier for me just to make it hard numbers, and then everybody just will have the same answer, and I'll tell you to round it off to like 1 decimal or something.
That's fine.
Okay.
Yeah.
Okay, so at this point, okay, quiz 1 was fine, correct?
Mm-hmm.
Yeah.
Okay, so it's quiz 2. Has anybody tried quiz 3 yet?
No.
Okay, so I'll work on quiz 2 this weekend and quiz 3 so that I'm a little ahead of the game. And then hopefully that will be the end of the frustration. Okay. All right, so.
Oh, one more question about that.
Sure.
Is there going to be due dates on those?
Oh, the due date on the quiz. Okay, first of all, you have to realize that a quiz, it's not really a quiz. It's an interactive learning tool because you get to take it 3 times, right? There's unlimited time. You can have your book with you. You can take it with friends. It's not like I'm really trying to assess anything. So I'm hoping everybody's just going to get 100% of the quizzes. In fact, I'll just say, if you take the quizzes, I'll give you 100%, whether you get a 0 or whatever. They're meant to be taken in the week they appear. So, in line with not getting behind in the course, you should take them on the week they appear. But, there's no issue with opening it up and seeing what the questions are because there's no time limit. You can actually log out of Canvas and keep the quiz open.
Definitely.
Yeah, so, yeah. I guess I will say that the quizzes that are before the midterm, definitely take them before the midterm. But ideally, you should be taking them in the week that they appear. Okay, so does anybody want to ask questions, or should I just start doing problems?
The only question I was uncertain about was the passive sign convention.
Okay, you know something? I'm so happy you asked about that because that is like the most basic, fundamental thing that you have to get right in this course. And if you don't get it right at the very beginning, you're just going to have a headache throughout. So let's, again, really make sure we get it. So, passive sign convention says this. Okay, first of all, what is this? And by the way, is this in the way? Better. What is this?
Sometimes circuit element.
Okay, I'm realizing I have to run to my office and get a marker because this is not going to last me through.
Over here.
Is there
Yeah,
one?
we'll watch it.
Oh, Okay, I think I can get through class with these kids. What is this?
Circuit element?
It's a circuit element. What is a circuit element?
An element of a circuit.
It's an element in a circuit. I love it. That's exactly what a circuit element is. It could be anything. We don't know what it is. It could be a piece of cotton. It could be my earring. If, you know, and where I just hook it up to some wires and I put it in the circuit, it's a circuit element. Now, those aren't very useful circuit elements, but it's just some blob, something that you put between two terminals or nodes. So you got to start learning this vocabulary. And what we're interested in is the voltage current characteristic, which basically means the relationship between the current through the circuit element and the voltage across it. Okay, so voltage and current have very specific definitions. Current, we know, is the flow of charge. You know, it's how many coulombs pass through a certain cross-sectional area in some amount of time. And so the units are coulombs per second, or an ampere. Voltage, the definition's a little bit trickier, but you must memorize it. I really want you to have a very deep, solid understanding of what voltage is. First of all, you can't talk about voltage unless you talk about two specific points that you're looking at the voltage between. So it doesn't make sense just to talk about the voltage here, unless you're talking about a node voltage. We'll get to that later. But a voltage always has to specify 2 points. So the voltage across a circuit element is always specifying the 2 nodes on either side, the 2 terminals. And so when we talk about the voltage across this element, we are talking about how much energy it's going to take to move a coulomb from one terminal to the next, or one point in space to the other. That's the definition of voltage. It's the amount of energy it takes to move a charge from here to here, from point A to point B. Now, usually we think about the charge going through the element to from point A to point B. However, it doesn't have to travel that path. It could go this way. It could go to the moon and back. And of course, as it goes through those different paths, it may travel through other circuit elements. But no matter what path it takes to get from point A to point B, is it going to be the same amount of energy that is required? Yes, the answer is yes. And that's why we can talk about the voltage between 2 points, is because no matter what path is taken, it's going to be the same amount of energy that will be required to get it from this point to this point, whether you go through the element or through some other path. Same amount. Now that's actually kind of surprising, or isn't it? Why is it that it will take the same amount of energy no matter what path you take?
The electric field is conservative?
Yes. Actually, yes, the electric field is conservative, or the way I would have phrased it is electrical forces are conservative forces. What does it mean to be a conservative force? Actually, it's kind of a circular definition because it means exactly this. It means that the amount of work it does in moving something from one point to the next is path independent, right? It doesn't matter what path you take to go from point A to point B, it's going to be the same amount of work. What other forces are we familiar with that are conservative?
Gravity.
Gravity. Then there's another one I think you learn in physics. An elastic spring force is also conservative. Is friction conservative? No. Okay, so friction is path dependent. It will matter. The amount of work done by a frictional force in going from A to B will be different if it goes through that path or some other path. So friction is not a conservative force. So we can't talk about voltage with respect to a frictional force. We can only talk about voltage with respect to electrical forces. So specifically, the definition of voltage is the amount of work or energy, whichever way you want to phrase it, it takes to move a charge from A to B. You know, some point A to some point B. And it doesn't matter how it moves, it's just if it gets from there to there, then it takes whatever the amount of energy that the voltage says it takes. So the units of voltage is volts, which is what? Just from the definition. Oh, that's good. Joules per, no, Coulomb. Because we don't really care about the time it takes. Okay. So the units of voltage are joules per coulomb. The units of current are amps, or coulombs per second. So now let's talk about power. Let's put some numbers on this. If the voltage here is 5 volts and the current is 3 amps, then what this is saying is that it takes 5 joules to move every coulomb from A to B. And if I know that there's 3 coulombs every second, then I know that there is 15 joules that are being expended every second. Okay, so this is the power that is, for now I'm just going to say happening, right? It's going to take 15 joules to move a coulomb from A to B. And so the most general definition of power for a circuit element is I times V. The passive sign convention, the only reason for its existence is to give us a common language for what we mean by positive power or negative power. So here's the deal. And I know that this isn't a common thing to see. In fact, I've never seen it, but I like putting a subscript on my power to designate whether it's being absorbed or delivered. And of course, since we're engineers, we're interested in the element. Well, is the element itself absorbing power or is it delivering power? The reason the sign convention is a little bit different than in your Physics 4B class is because physicists are more concerned about the electron, right? They're not concerned about the element as much as they are about electrons because they're physicists and they're more like basic fundamental scientists. We're engineers and we want useful devices, and so we're concerned about whether or not the element is absorbing or delivering power. But of course, if the electron is delivering power, that means that the element's absorbing it. Anyway, that's why you get the confusing opposite like signs from your physics class to your engineering class. So sorry about that, just try to bear with it. It does have to do with, you know, what's more important to each person. Okay, so in this class, we're concerned about the element. We want to know what the elements are doing. Are they absorbing power? Are they delivering power? So here's the passive sign convention. When the current is pointing into the positive terminal of the voltage, power is being absorbed. Okay, so why did we choose to say it that way? I don't know, somebody decided that that's what we mean by power absorbed. Power delivered is when you have the opposite, right? So if this is the power absorbed, the power delivered is going to be minus 15. Which, oh, and by the way, joules per second is what unit? Watt, yeah. So it's a little bit awkward because sometimes you don't, well, most of the time, you don't even see these subscripts. So you're the one that has to keep track. That's why the passive sign convention is kind of confusing, is because if I don't have these subscripts, I'm saying, oh, the power is 15 watts. Well, here the power is minus 15 watts. They're both right. But you just have to understand that in this case, the power is being absorbed. In this case, it's being delivered. Okay? So that's the passive sign convention. Did that help? I hope. Yes.
I just have a question. So suppose they give us the current coming out the negative node. Can you just?
Well, do you mean like this?
Yeah, because a lot of
that's the same thing, though, right? This is the same as that. You're just.
Exactly. That's what I was just gonna.
Yeah. That is. It's exactly the same. Okay.
That's what I figured.
Good. So now let's do some other exactly the same things that get a little confusing. So, okay, so we all agree that this is really the same as this, it's just where you're placing it, but it's still having current going into the positive terminal. If I turn this around, is that exactly the same thing?
No.
No, it's not the same at all. If I put a negative sign there, now it is exactly the same. So, and a lot of times we don't know what the current is, and so we're just going to call it I, like probably we'll put a subscript on it for a specific current, I1. I1 is the current that's leaving the positive node. Well, what's the value of it? It could be negative, and if it is negative, then it's negative. That's just how it is. But if it is negative, then what it really means is that a positive charge, well, if the actual value of I1 was -3, then when you have the arrow pointing this way, the -3, so you've really got a positive current. Okay, so there's all those like switch-arounds that you have to be comfortable with, because we don't always know what the value of current is. So this is exactly the same as this, where I is some number, and it could be a negative number. Yes?
So even though we change that, we still keep the plus and negative sign?
Because current and voltage are independent. I mean, they're related to each other, but at this point, we're not sure how they're related. So we're just going to show current. The important thing is that whenever you show current, you have to show a direction and then some symbol. If you don't, if you know the number, then you put the number down. But if you don't know it, then you put some unknown variable, I1, and then we'll figure out what that is later. Here, if we don't know what the voltage is, we just have to call it V. And we can never show V just with V. We have to show a positive and a negative. Have to. So they're kind of like vectors in that sense, in that they have both magnitude and direction. Well, current has direction. Voltage has direction too, but we don't exactly call it direction. We call it polarity. It's, which side the positive and the negative are on. All right, so, and then there was a handout, in fact, somebody posted a question about it, where there's a way to talk about this. It's like A is, well, let me put the number back on, 5 volts positive with respect to B, or you could say that B, terminal B is 5 volts negative with respect to A. Did you learn that vocabulary? Yeah, I mean, it's just a way to talk about it that you have to become familiar with. Here it can even get a little bit more confusing. Let's say that we know that the actual value of this voltage is -5. What does that mean? Well, the way we have to say it is that A is -5 volts positive with respect to B, which is a crazy way of saying it. But we'd be forced to say it that way if we saw the picture like that. Or we could change the picture, right? Change the polarity and then put the negative of that value for the voltage. So now this voltage here is positive 5 volts, in which case we would say that B is 5 volts positive with respect to A, which is the same as saying A is -5 volts positive with respect to B. Yeah, it gets a little confusing, but try to really get it solid now so that when we get into the harder problems, it'll just come naturally and automatically. All right, so that's the passive sign convention. That's it. It's just telling you what it means for power to be absorbed or power to be delivered. And the definition of power absorbed is that when you have the current going in, pointing into the positive terminal of the voltage, You calculate the power absorbed by just taking the value of that current times the value of that voltage. One of those values might be negative. If that's the case, then you actually get a negative number, and that's fine. You just carry the negative. If you don't like it, you could turn it around and say, okay, the power delivered is positive. But sometimes you don't have that choice. Sometimes you're kind of forced to just deal with what you've been given, and so you might have to end up saying it in a more awkward way. Okay, so I want to talk a little bit about those circuit elements. So, circuit element, and we're always interested in what I call the voltage current characteristic of a circuit element. All that means is, what is the relationship between the current through the element and the voltage across it? Because there's always going to be a relationship. And the first relationship that you come across is for the specific element of a linear resistor. Okay, so there's our first circuit element. And the relationship between the current and the voltage for this, we all know, follows what we call Ohm's law, V equals IR, where R is just some value for the resistor. If I ask you on a test, what is Ohm's law? It is insufficient for you just to say V equals IR. The reason being, both V and I have, are kind of like vectors, right? They have magnitude, but they also have a direction or a polarity. So this has got to be attached to this picture. Has to be. V equals IR. So this is what we call the voltage current characteristic for a linear resistor. So I'm sure you knew that before today, but now there's more sophisticated language to use. Okay, so that's our first circuit element. I'm going to give you 4 more. Okay, so here's another circuit element, and the voltage across it is what I've labeled here Vs. This is a voltage source, okay? So our first circuit element was a resistor. Our second circuit element is a voltage source, which means that it can supply energy to a circuit. And the voltage current characteristic for this source is, anybody know? So if I were going to plot this, it would look like this, right? V versus I. What would it look like here? Damn it.
What is that? Constant voltage.
Yeah, it would just be like that. So it's just, I mean, it's kind of a weird voltage current characteristic, but Vs is just some value, like, whatever value it is, maybe 120 volts. You may or may not know what the value is, but it's some constant value. Okay, so this is called an independent source because it's independent of the current through it. No matter what the current through it is, it's going to, sorry, I should have put that S on here. Whatever the current is, it's going to deliver that voltage. That's what it means to be an independent source. Okay, so this is called a linear, so let's name these. Linear resistor, and this is an independent voltage source. I'm going to abbreviate, is that okay? And this is how we show it. And what we're always interested in these circuit elements is what is the relationship between the voltage across it and the current through it, and here's our answer here. Similarly, we can have an independent current source. and it looks almost exactly the same. But it delivers a current instead of a voltage. And so the relationship between the current and the voltage in this case is that the current is some value. So if you were going to plot it, it would look like that. Right? Because no matter what the voltage is, whoops, sorry, I forgot the S again. And of course, that's kind of an awkward way to look at it. Oftentimes, you'll switch the axes and look at it like this, in which case it kind of looks the same. But the idea is the same, right? No matter what the voltage is across it, the current is going to be constant. That's what it means to be independent. For a voltage source, it means that it's going to deliver this voltage no matter what the current is. In other words, no matter what it's hooked up to. Here, it's going to deliver this current no matter what the voltage is across it. Question?
So I'm still, right now I'm still messing up with the capitals, letters, and small letters.
Okay, thank you.
So basically,
I'm
constant?
Yeah, I did like kind of intuitively do this capital because it is constant. But when I have it as a small v, it basically means I don't really know what it is. It might be vary with time, it might not, I don't know. But usually the convention is that the small case letters vary with time. So this is still a variable. I don't necessarily know what it is. Sometimes that's what you'll be asked for in a problem, is to figure it out. But if it's capital, at least I know it's constant. It doesn't vary with time. And notice I wasn't consistent here. If this were constant, I should have labeled it capital IS. So anyway. All right, so those are two more circuit elements that we've learned. We're going to learn two more, actually 4 more. Anything with a diamond like that is a dependent source. Okay, and there's actually 4 categories of a dependent source. You can have a current-controlled voltage source, a voltage-controlled voltage source, a current-controlled current source, or a voltage-controlled current source. So in other words, this might be a voltage source, and instead of drawing 4, I'm just going to keep erasing. Sorry. Or it could be a current source. If it's a voltage source, the fact that it's dependent means that it might depend on some current or voltage somewhere else in the circuit. So this might be hooked up to some complicated mess, and maybe there's a resistor somewhere in this complicated mess. And I'll label the current through that resistor IR, and I'll label the voltage across it VR. And so if this is a voltage-controlled voltage source, then the voltage here might be shown like that. So what this means is that the voltage that this delivers depends on this voltage here. So it's a voltage-controlled voltage source. So we see it's a voltage source because it's got the plus and minus. And the value of the voltage that it delivers is just going to be whatever the voltage is here times some constant. Sometimes this is called the gain. What are the units of K in this particular case?
No units.
No units, exactly. Because it'll deliver a voltage, so that, VR is a voltage, so you just multiply by K, you're getting volts. What if this was a current-controlled voltage source, and so it happened to depend on the current IR? You know, it's just some other current in the circuit. I'm just kind of showing a particular branch in the circuit and saying, okay, we've got a current through that branch called IR, the voltage across that branch is called VR, and so now I'm giving you an example of a current, why do I have two R's there? Current-controlled voltage source. So that's the first one there, the current-controlled voltage source. So this is called the controlling quantity. Okay, the current that it depends on is called the controlling quantity. Learn this vocabulary because I'm going to use it and it's going to become really important for you just to know what I mean by controlling quantity. In this case, what are the units of K? What do they have to be in order to work?
Current.
Volts per amp.
Volts per amp, exactly. Everybody see that? The units of K have to be volts per amp. So here you have a constant that has units. With the voltage-controlled voltage source, the constant didn't have units. But usually you don't even show the units and you just expect it to work out. The confusing thing about this picture is you look at this and it looks like a current. It's not. This is not a current, it's a voltage. Okay, and then should I go through the current source or it's pretty much the same? Let's skip that. Unless, well, I'll just do a little test. If I had this, okay, what's the name of that?
Voltage controlled current source.
Yes, it's a voltage controlled current source. What are the units of K?
So that value needs to be a current?
Well, it actually needs to be a current over a voltage so that
Right,
the
like,
multiplication
the
of
whole
these
thing
two
should be-
things give you
should be
amps. Right, so K actually has to be amps over volts. I guess that's all. All right, okay, I do want to do a problem, but one more thing before I do the problem is, well, actually two more things. If I label the voltage across this, I'll just label it V1. What's the relationship between the current, this current, which is K times VR, and this voltage V1?
Depending on whatever network is connected.
Yes. It'll depend on what it's hooked up to. But the point is that no matter what it's hooked up to, you know, V1 might change, but this will never change. It'll be delivering this current. So that's what it means to be ideal. Okay, so I think I ended last week just kind of saying, try to really get a handle on what it means to be an ideal source, and then what it means to be an independent source, and what it means to be a dependent source. So an independent source means that this voltage does not depend on any other voltage or current in the circuit, including the current through it. The dependent source does depend on some voltage or current somewhere else in the circuit, but if it's a current source, it's not going to depend on this voltage. This voltage can be anything. So that's what it means to be ideal. All of these sources are ideal. The only difference is that the dependent ones might depend on a current or voltage somewhere else in the circuit, but it doesn't depend on the current or voltage through the actual element. So ideal source does not depend on voltage or current in the actual element that you're looking at. And I'm phrasing this a little bit different but simpler. I'm just not sure if it's clear. So what I'm saying is that, so if you have this voltage controlled current source, this, if it's a dependent current source, it's not gonna, it can't depend on that voltage. It might depend on some other voltage somewhere else in the circuit, but not on the voltage in the actual element. Okay. Okay, so let's do this problem. Anybody want to ask a question before I do a problem? Okay, so let me just say that what you should take away from this session is really understanding what it means to be a circuit element, just a general blobby circuit element, right? It's just something between two nodes. And the thing that you're interested in is what's the relationship between the voltage and the current. The voltage across those two nodes and the current through it. That's called the voltage current characteristic. And for a resistor, if the voltage current characteristic here were V equals IR, then we would know it's a resistor. Okay, I might not be able to. And then just the idea, make sure you really understand the idea of the different sources. What it means to be ideal, and then what it means to be independent, and what it means to be dependent. One important thing to remember is that all the sources, both dependent and independent, all of them are ideal. All of them are ideal. Okay. Is this visible? No. I feel like okay, so here we have a circuit. Got some switches here. Oops. So this is called a make before break switch. Sorry about that. This was supposed to be straight. But... All right, so this closes at 3 seconds. So it's hooked up here, but then after 3 seconds, it switches to a position here. At 2 seconds, this switches, that's connected, from basically this node to this one. Okay, and that's 2 amps. Okay, so what we have to do is determine the voltage at 1 second and at 4 seconds. And determine the voltage here. Okay, so at 1 second, let's see. Well, at 1 seconds, neither of these switches have moved. So the circuit actually looks something like this. So we've got 1 amp coming into this node from this source, 2 amps coming from this source. So by Kirchhoff's current law, right, how many amps do we have going through that? 3. That's a really trivial question, right? So, okay, this is supposed to be an ohm. Well, you can get it from this picture. This resistor is 5 ohms. So by Ohm's law, V equals IR, and do we have it pointing in the right direction? Okay, because remember, this formula, V equals IR, doesn't make any sense unless you have a picture and you know the direction of I and you know the direction of V. So does this voltage current characteristic match the picture? Yeah, we do. It goes according to the definition of what I erased where I said what the voltage current characteristic is for a linear resistor. You've got the current pointing into the positive terminal of the voltage, and when that's the case, you just plug in the numbers. You can calculate it. So in this case, V is going to be 3 times 5, 15 volts. Sorry. Okay, it is a little confusing because the actual unit of volts is a capital V, which looks really similar to the small case v, which is the variable for the voltage across that element. So you know what that means. Your handwriting has to be really neat so that we can tell the difference between a big V and a small v. And also when we start putting subscripts on, I really want those subscripts to be legible. Please. Okay. So at 4 seconds, sorry, let's see, what does this look like? This is in this position, so it's like this is, I'll just show it. This is like open like that, and this is connected like that, and then this is connected here. So, So what's going on now? What's the current through that resistor? It's 0, because current has to have a path to travel. And if it doesn't have a path, then it's 0. So this is actually considered an open circuit. You know, from this point to this point is considered an open circuit because there's no path for current to travel. So there's some more vocabulary. And you should, I'm going to show you different ways to think about an open circuit. So what I just said is one of the ways. An open circuit is when you have 2 nodes and nothing's connecting them. Nothing is connecting them. That's one way to think of an open circuit. Sometimes it's a little confusing to think about it that way, so you could think of an open circuit as a current source where the current is 0. So you're basically forcing the current to be 0 in this branch by showing a current source with 0 amps. Sometimes that's a helpful way to think of an open circuit. And then the last way you can think of an open circuit is with a resistor whose resistance is really, really, really large, basically infinite. So if you have a resistor with an infinite resistance, you know, I equals V over R. So if this is really big, I is going to be 0. So those are 3 different ways to think of an open circuit, where you just have the 2 points are not connected, but then you're forcing the current. But the equivalent way to think about it is that you have a current source here which is 0. Okay, so then that would mean, so that's how I figured that the voltage here is 0 because there's no current. There's no current through the resistor, the voltage is 0. Okay, and then the opposite is a short circuit. So here you can think of a short circuit as just being where the two terminals are connected by a wire. And by the way, whenever you have two terminals connected by a wire, well, I'll talk about this next week, you can kind of collapse them sometimes so they're just one point. So you can change a circuit to look like whatever you want it to look like by stretching wires or collapsing them. And you haven't changed the electrical relationships. You might have changed the physical looking of it, but not the electrical relationships. Okay, so a short circuit is represented by a wire. So if I just connect anyway, that would be a short circuit. And then similarly to the other two ways that you think of an open circuit, how can I think of a short circuit besides just a wire that's connecting the two nodes? How about a voltage source that has 0 volts? Anyway, so that was similar to a current source with 0 amps. And then the last one, instead of a voltage source with 0 volts, how can you think of a short circuit? Well, instead of a resistor that's infinite, it would be a resistor with 0 ohms. Okay, so you kind of get the idea that there's, from what I've done today, that there's kind of always like a dual of something. Like we have the voltage-controlled current source, but we also have a current-controlled voltage source. They're considered duals of each other. Mathematically, they're going to be pretty much the same. Similarly here, we've got an open circuit. The dual of it is a short circuit. Instead of a voltage source of 0 volts, it's going to have a current source of 0 volts. Or instead of a resistance of being infinite, it's going to have a resistance of 0, which is the same conductance. Did you learn the vocabulary word conductance? It was in the reading. Conductance is basically just the reciprocal of resistance. So if the resistance is 0, the conductance is going to be infinite. So the dual of resistance is conductance. The dual of voltage is current. There's more duals, but that's different. Oh, the dual of parallel is series. The dual of a capacitor is an inductor. Anyway, and what that means is that if you just replace a circuit with its dual, the mathematical relationships are exactly the same. All right, I guess that's enough for this week. Feel free to come and visit me in my office hours or make an appointment if you can't do that. And hopefully this helps. We'll see if that video worked.